Hello, everybody, and welcome to You Can Finish the Sentence Right AP Chem video. How are you guys doing today? I'm kind of tired. I'm hungry. Why do I do these right before lunch? I don't know. But anyway, today we are going to learn about common ion effect. I'm going to tell you right now, this is a complete extension of Chapter 14. So you're going to see a lot of familiar things here. First of all, the common ion effect, in a nutshell, is basically a shift in equilibrium. And it's caused by adding a salt that has an ion in common with ions already dissolved in solution. We're going to define that more clearly in a minute, but for now, the big idea is that the common ion effect suppresses or stifles or basically causes a pH change not to happen like it normally would. Alright, so basically, we're talking about shifting equilibrium, so you can probably guess whose principle is going to be really huge here. Hopefully in your mind, you're thinking of bum bum bum, Le Chatelier's principle. That's all this is. Of course, we're going to put a lot of math to it too. All right, so let's take a look at an example. So we're going to look at our favorite weak acid, acetic acid, or CHACU. Okay, so HC2H3O2. I want you to write out the dissociation for this acid. So you go ahead and do this, pause the video. Okay, go ahead and write it out, but when it's all said and done, here's what we're looking at. So acetic acid, got your double arrow, and it's going to produce an H+, and then the conjugate base, the acetate ion. Okay, and the Ka, I bet a lot of you guys have this memorized, for this particular equilibrium is 1.8 times 10 to the negative fifth. All right, so here's the question. This is common ion effect. What would happen if you added some solid sodium acetate? So this is our salt. Now the sodium, we don't really see sodium in this equilibrium. You can probably guess that, as is often the case, the sodium is a spectator. So we're focusing on the acetate ion. So basically, you're sprinkling in some acetate ion. So that's not going to affect this guy, not going to affect this guy, but this guy. This is the acetate ion. It's going to go up. So if the acetate ion goes up, which way is this equilibrium going to shift to get rid of that addition of acetate ion? Hopefully in your mind, you're thinking that it's going to go this way. The classic example of Le Chatelier's principle. So some questions from this. If this happens, would you produce as much H+ as you would if you didn't add that salt? So if it's shifting in the backward direction, that means you're eating up some of that H+. So hopefully you were thinking in your head that you would not produce as much H+. Likewise, what's going to happen to the pH then? So if you're shifting in the backward direction, you're producing less H+, you're going to have less acidity. So the pH is going to go up. So in other words, pH is going to become higher. Less H+ means less acidic. Hopefully that's pretty much common sense. Well, guess what? That's basically common ion effect, and as you're going to see later, this is what buffers are all about. Now we're going to do some calculations to support what we just did. First one, over here on the left, it says calculate the pH of a 0.3 molar acetic acid solution. This is like a baby ice table. This is nothing fancy, but we're going to use it for comparison's sake. So I want you to go ahead. Here's your equilibrium, the one that we had just written out earlier. Set up your ice table, use the Ka value, and I want you to calculate X, and then from that calculate the pH. So pause the video, do this calculation, and when you're done, go ahead and check the answer. Waiting. There's the answer. Okay, so we solve for X, nothing fancy here. The pH is 2.63, which is pretty typical for a weak acid solution. Now, I also added this, so I want you to write this down too, the percent ionization. Percent ionization, as you well know, is concentration of H+, or basically X, divided by the initial concentration. So for this particular weak acid solution, it dissociated by 0.77%. Okay? Well, now what we're going to do is the exact same calculation, but this time we have our 0.3 molar acetic acid solution, but there's also a 0.52 molar sodium acetate in that same solution. So we have the presence of a common ion. Well, what you're going to see is that we're going to handle this exactly the same. So there's our classic dissociation. Nothing has changed. It's the same exact reaction. But this time, we're going to have a value for the initial amount of acetic acid, but we also have a value for the initial amount of acetate ion. So that's the key. So when you set up your ice table, it looks a little bit different. 0.3 goes here. This is still 0, but this is 0.52. So you actually have a value over here instead of being 0. Now, this equilibrium is still going to shift in the forward direction. Since you don't have any H plus, you absolutely have to make some H plus, so it's going to go forward. So this is going to go down by X, this is going to go up by X, this is going to go up by X. All right, so now these would represent your equilibrium concentrations, and just like you've done in the past, we'll go ahead and solve for the Ka expression. All right, of course, when you get to this point, there's some opportunity for simplification. Is it safe to say that the Ka value is small enough that X is not going to be significant compared to 0.52 or compared to 0.30? Absolutely. Furthermore, because this has been raised, this equilibrium is even going to shift less in the forward direction because of the common ion effect. So for both those reasons, we can definitely get rid of this plus X, and we can definitely get rid of that minus X. All right, so go ahead and do the math. 0.3 times this divided by 0.52, and hopefully you get this X value. All right, you can then get the pH. Okay, so the pH is about 5. All right, this is pretty different from 2.63. Just like we did in this example, I want you to calculate the percent ionization as well. So H plus concentration over the initial. Well, this guy, with the presence of the common ion, only dissociated 0.0033% compared to the 0.77. Okay, so with these two examples, this clearly shows the effect of the common ion. The solution does not get as acidic as it normally would, and the percent ionization is not as high as it normally would because of the presence of the common ion. All right, fun times. Now what we're going to learn is a different kind of simplification. There's this formula, it's called the Henderson-Hasselbalch equation. Oftentimes when we're going through the unit, we'll just say, we'll call it HH, the Henderson-Hasselbalch HH or H squared equation. All right, we're going to sort of derive this. We're going to do this once. This formula that we're going to derive is actually available on your equation sheet. All right, so the first thing is we're going to start with the Ka, like we did above. So if I switch back real quick, Ka equals H plus times the A minus over the original acid. So we're basically just starting with that Ka expression. What I want you to do is rearrange it so that you solve for H plus. So do a little bit of algebra so it's H plus equals the rest of those variables. Give you a second to do that, okay? And now you can check your answer. So we solve for H plus, okay? Now what I want you to do is we're just going to logify everything. So I want you to take the log of both sides. So when you do that, it looks something like this. So, and by the way, that was the negative log of both sides. So the negative log of the H plus, and then I'm going to separate the constant, the Ka, from the variables that actually change. So therefore, it's the negative log of the Ka, and then the negative log, and I'm going to keep this together as sort of a ratio, so the negative log of the HA concentration over the A minus. We can further simplify that. Hopefully when you see negative log of H plus, that makes you think of something. That, of course, would be pH. Negative log of the H plus is a pH. Now, negative log of the Ka, we haven't seen that before. But you can take the negative log of anything. But what would you call this? Well, negative log of the H plus is pH. Negative log of the Ka would be pKa. And then, you know what? We really don't like that negative sign. If, you know, it's just more simple if we can change it to a positive. So if I switch that to a positive, then what happens is I actually have to flip the top and the bottom. Okay, and if you've studied logs, you kind of know that. So basically that's what we're looking at, the log, and now it's the base over the acid. This, my friends, is the Henderson-Hasselbalch equation. It's on your equation sheet, and it's something that you want to remember. The basic idea is it's pH equals pKa, which is the negative log of the Ka, plus log, and it's always, 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 always base over acid. All right, so can you go back to the example above and use the Henderson-Hasselbalch to solve this problem? So what would that look like? So in the end, we want the pH, right? So let's take a look at how that would look. We're going to take the pH, that's what we're looking for, the negative log of the Ka, so that's the Ka for acetic acid, plus the log of the base, which in this case is the conjugate base, the sodium acetate, over the concentration of the original acid. And these are the original values because remember the minus X and the plus X doesn't really contribute anything. So go ahead, I need you to do this. I need you to punch this into your calculator, make sure you're punching everything in correctly. and you should come up with about a pH of 4.98, which is very close to the pH of 5 that we got earlier. So there you go. That's the Henderson-Hasselbalch equation. All right, now, last but not least, why would you use a Henderson-Hasselbalch? You're going to see that we're going to use it a lot in this chapter. And basically, there's one thing that you need. You got to start off with a weak acid. I'm going to tell you, you're going to learn in no uncertain terms that this does not apply to strong acid or strong base situations. When you start off with a weak acid or base and its conjugate, they both have to be present in the solution at the beginning. If that's the case, then you can use the Henderson-Hasselbalch equation to solve for pH. I will tell you that using the Henderson-Hasselbalch equation is nothing more than setting up the ice table just like we did here. Okay, and you don't want to lose track of that. Let's see, last but not least, so this whole common ion effect, where is it going? It's this application called buffers. So just to summarize, a buffer solution. A buffer is a solution of a weak acid or base, and it's got to be weak, and its conjugate partner. Okay, so that's the definition of what a buffer is. A buffer is basically a common ion situation. So a buffer solution suppresses or stifles a pH change, okay, when strong acid or strong bases are added. All right, now you guys have heard of buffers. I bet many of you guys have heard of maybe buffered aspirin, okay? Since it kind of doesn't cause big pH changes, it's better for your stomach. So buffered aspirin is better than regular aspirin for your stomach. You know, and then in your body, if you guys are taking anatomy and physiology, I guarantee you've talked about buffers with keeping the pH constant in your blood, okay? And there's some other applications too. I think hiccups is kind of a fun application. Just to give you guys an idea, you know what? When you hiccup, right, you're basically, this pH, or this equilibrium is basically going on in your body. So in your bloodstream, you got to be real careful what your pH is. You don't want it to deviate a lot. If this H plus goes too low, that's sometimes what causes the hiccups. So when you're hiccuping, basically it's causing your body to take in more CO2. So when you hiccup, okay, you're just forcing your body to keep breathing in, okay, and that CO2 level goes up. When that CO2 level goes up, that kind of reestablishes or gets your H plus back where it needs to be. So that's kind of fun because, you know, sometimes if you want to get rid of the hiccups, what kind of things do you do? Breathe into a bag, right? That's me breathing into a bag, by the way. Okay, when you're breathing into a bag, you just basically keep breathing back in that same CO2. You're not getting like fresh air. So again, that increases your CO2, which makes your H plus higher, and that hopefully gets your blood pH back where it needs to be. So it's kind of a neat system. There's lots of interesting discussions about hiccups, and we'll talk more about that in class. All right, that basically concludes our video for today. We're going to go into how buffers actually work tomorrow, so be ready for that. If you haven't read 15.1 or 15.2 in your book, you need to. Thanks for listening.